Welcome to Cafe Calculations. My name is Eric, and this is a continuation on the building blocks to half of calculus, which is the derivative. In the last video, I started by showing you the average rate of change. That is going to be used in principle to build what we call the instantaneous rate of change. And this would be equivalent to if you're sitting in a car and you accelerate onto the freeway, every slice of time from time equals 0 to the time you're going at a cruising speed is a different rate of change. This is where calculus comes into play and allows us to calculate what would be that instantaneous rate of change at any moment in time. And this is how we first have to build up the derivative to be able to allow us to do this. So without any further ado, let us build up the instantaneous rate of change of the derivative. So the first thing we're going to start with is going to be very similar to how we started the average rate of change. The only thing different, I'm going to draw my function, f of x, which in this case will be our parabola x squared. And once again, I'm going to draw my 2 points. This one is going to be the x1. This one is going to be, again, the x2. We're going to do the same thing we did last time. We're going to connect the dot between the two like we did with the average rate of change. So we're connecting these 2 points. And as you see, the dotted line does not hit every single spot of the f of x curve, the parabola. So this is where we bring in the calculus element. So if we're trying to calculate the instantaneous rate of change, meaning at one particular point in x, what is the rate of change of the y, or the f of x in this case? This is where we bring in the idea of limits. At this point, I assume you have a basic understanding of limits. I will not be going too detailed into that. That'll be for a different video. So right now, we're going to build up the same idea from the average rate of change using the structure of the slope, but we're going to add the limit to it, which will get us to the instantaneous rate of change. So let's do it. So the first thing we want to do is have our delta y, which is the difference in y's. Well, the y of this is going to be f of the x2 coordinate. So that's going to be the y2 as we learned before. So that's really f of x2 minus the other y, which is the first y, f of x1. That's our delta y. Now, over the difference in x, I'm just going to write that as delta x, which is the difference between the x coordinates. Now here comes the calculus element. The calculus element is our good old friend, the limit. Now he's old to me, but he may be new to you guys. The limit, in a general sense, is what is the function tending towards as we move towards values in x. So as I move towards values in the independent value, where is the y value tending towards? Not where it's going to be, but where is it tending towards? So we're going to ask what happens as we take the limit as the delta x approaches 0 of this thing. Well, let's draw another picture and see what happens when the delta x goes to 0. So we're going to redraw our parabola over here. We end up on top of each other with 1 point. And now we see that this line, or the dotted line, is now what we call tangent to the curve at this particular point, x. This is going to be the instantaneous rate of change at that particular point of x. Now here's something to keep in mind. Normally when you take a derivative, generally speaking, you're going to end up getting back another function. It doesn't always happen, it depends what the function you started with. But normally you get back another function. So now let's formally write the full definition of the derivative in its mathematical sense. So we're going to call f prime, the f prime stands for the derivative of f of x, excuse me. Or we could say the rate of change of f of x with respect to the variable x is going to equal the limit as delta x approaches 0 of our f of x plus delta x. Now the reason why I write this in general with the delta x is I'm at some general value f of x, but the second y coordinate is a little bit further along, whatever that number would be. I'm going to generalize that by just saying it's a little delta x more away, minus the original y, which we're just going to call f of x. This way we can have a generalized function for the derivative all over delta x. Therefore, our first principle derivative, and what I mean by that is this is the mathematical engine under the hood. This isn't the most slickest way to do it or the most efficient way, but this is the way you have to learn first so you understand the machinery underneath the mathematical procedure. This is known as the limit definition of the derivative. Thank you very much for watching CAFE Calculations, and I hope to see you very soon in our new episodes. And remember, enjoy the process.